right, one last calculation here. This one is commonly missed. We kept saying that when you see degrees Celsius, at some point you want to use that equation, mass times temperature change times specific heat. And we do. But there's something a little tricky about this particular question. So here's what's wrong. Warning, this is wrong. But common mistake. People are kind of on autopilot, and they'll say delta H equals mass. And we know for water the density is 1, so 85 milliliters would have a mass of 85 grams. Temperature change, they'll say final minus initial, 100. And then somehow they'll add in the specific heat. Specific heat, they'll look it up on a chart, plug it all in, and be done. Here's what's a little tricky, especially if the substance is water, which we're expected to be pretty familiar with water. Between 50 degrees and 150, you're going to go through a phase change. And often, if you just leave it at that, you're getting the energy required to change the temperature, but you're not adding in all that heat energy required to boil the liquid water at 50 degrees and change it to steam at 150. So with water, be careful of the temperature range. If you're going through 0 or 100 degrees, you have to add in the amount of energy required to change the phase. Super common mistake. So I really want to think about this as kind of a phase graph, where we're changing the temperature through the solid phase, then melting, liquid, boiling, gas. So if I'm starting at 50, I'm maybe like halfway through the liquid phase. There's my 50. Then I'm going to bring it up to 100. Here we'd be at 100 degrees, the boiling point. And then we got to go up maybe another 50 degrees through the gas phase. So I kind of want to think of it as 3 separate calculations, and then we'll add them all together. Okay, so first thing we need to do is increase the temperature of the liquid. If we're increasing the temperature, yeah, we can do delta H equals the 85 grams. This will just be a 50-degree temperature change through the liquid phase. And then I want specific heat of the liquid. Remember, water is kind of goofy in that it has a different specific heat depending on its phase. So for liquid, 4.18 degrees Celsius. Okay, so that's for the liquid. And then we just plug it all in. And with reasonable significant figures, oh gosh, I don't know, maybe we can round it to something reasonable in the end. 17,765. 65. And that would come out in joules. Okay, so here's one of the numbers that I'm eventually going to need. Next, I need to boil this sample of water or vaporize the sample. So we're in this section of the graph. There is no temperature change, but there is a significant energy change. So the equation that we'll use is that moles times heat of vaporization, which I guess then we need to calculate moles. Not a big deal. 85 grams, it is water. Let's cancel grams, put her in moles. We never escape the mole. Water's molar mass is about 18.02. So we'll divide those, and we're looking at about 4.72 moles. Then the heat of vaporization is a constant. That's something I can look up on a chart. And I got it for water. So we're going to take our 4.72 moles, multiply by the heat of vaporization. 40.6 kilojoules per mole. Alrighty, so I'm sitting at around 191.6 kilojoules. But eventually, if I'm going to want to add these values, I need them all in the same unit. Specific heat gives you joules. Heat of fusion and vaporization give you kilojoules. So maybe I'll just switch this to joules right away. That'd be easy. 191,600 joules. Whoopsie, that's not a joule. Joules. There we go. Okay, so I'm going to use this guy. So that if I add them together, they're all in the same unit. That is a significant amount of energy that you're missing out on if you just go mass times a total 100-degree temperature change times specific heat, which now looking at the graph, what specific heat would you use? For water, there's a different specific heat for the liquid phase and the gas phase, but you're missing out on this phase change. It's a significant amount of energy. It's almost 2,000 joules worth of energy. So if you're doing these, like there's one in the homework, and people always come up and they're like, I just can't get the right answer. I'm way off. 99% of the time, this is it. Oh yeah, that's a lot of energy you're missing. Now we can do the top section and we're good to go. We're all in the gas phase now, so we can increase the temperature that last 50 degrees. We got 85.0 grams. We're going 50 degrees through the gas phase. And then for water, I need specific heat of the gas. 2.042 joules per gram degrees Celsius. So that's for the gas phase. And these constants, heat of fusion, heat of vaporization, specific heat values, I'll give them to you. I'll even give you all these equations for the test. We just need to know which one to use and how to use it. All right, let's plug it in. So maybe like 8,679 joules. There. By far, that phase change required the most energy of all sections of the graph. Because now you're not just making the particles move faster, you're trying to overcome all of those intermolecular forces. Think about how many water molecules are in an 85-gram sample. I mean, if we wanted to, we could take that 4.72 moles, multiply by 6.02 times 10 to the 23rd. That's a lot of molecules. That's a lot of intermolecular forces to separate. By far, that one takes the most energy of all sections. But now we got this. All we need to do is add them. So we'll just add them together. Oh, let's see. So we could say like 218,044 joules, or maybe with a more reasonable amount of significant figures. Like, yeah, 218,000 would be good. Or if you wanted, you could even say 218 kilojoules total. Got it. And again, I'm not going to pick too much on sig figs. Often on a big problem, they might suggest like round your answer to 3 sig figs, 4 sig figs. 3 might be kind of reasonable here. We've got like 85.0 grams. That would be reasonable. This is a great question. Where for water, we need to recognize that if we go through 0, we're going to do the melting phase change. We've got to add all that energy in. Or freezing if we're cooling the substance. And if we're going past 100, we're either boiling or condensing. We need to add in that heat of vaporization.